Friday, we started learning how to add vectors together. We'll spend a couple minutes talking about the easy vectors, how we added the easy vectors together. The vectors that we learned to add together really in grade 5 or grade 6 without realizing we were really adding vectors together. Vectors like this. If I have a vector that's 3 meters to the east and 4 meters to the east, that's an easy one, right? We add these two vectors together, what are we going to get? 7 meters, right. You can see the 3 meters is drawn as a vector. It's a line with a little arrow on the end of it. Okay, the 4 meters is the same thing, a line with a little arrow on the end of it. If I want to draw the resultant vector, which is the sum of these vectors, it's these vectors added together, then what I want to draw is a vector diagram. Now, this is an easy vector diagram as well. I'm just going to draw like 3 meters and 4 meters like this, just drawn head to tail. You can see the head of the first vector, the tail of the second vector. That's my vector diagram. My resultant vector, which is my vector that is the sum of the vectors, is just drawn from start to finish. 3 plus 4 is going to be equal to 7. Easy, right? Easy. Now, the reality is, I wouldn't even ask you to draw a vector diagram for this one, right? We could draw the vector diagram, but we don't need to. We can do this one in our head, right? 3 plus 4 is equal to 7 because they're both in the same dimension, both on the x-axis, and both in the same direction, both to the east. Now, this next one becomes a little bit harder. Not bad, right? This is still a grade 6 problem, although you didn't necessarily realize in grade 6 you were adding vectors when you did problems like this. Okay, I've got 3 meters to the east here, 4 meters to the west. Again, the 3 meters is drawn as a line with an arrow on the end of it, so is the 4, but the 4 meters is drawn in the opposite direction. The vector diagram here would look something like this. 3 meters, and then it's kind of hard to draw the next one because it goes back upon itself. 4 meters. The resultant vector, or the sum of these vectors, is drawn from start, which is right here, to finish, which is right here. How do I find this one? Again, you don't really need to draw the vector diagram because you could probably do this one in your head. We would say 3 plus -4 gives me -1 meter, or we would say 1 meter to the west. So adding vectors in one dimension is not really that hard. It's adding positive numbers together, or adding negative numbers together, or adding a positive to a negative. When all is said and done, we don't really need to draw that vector diagram, but if we do, we got to make sure that we draw them head to tail and the resultant vector from start to finish. That resultant vector, remember, is the sum of those vectors. Easy, right? Well, a little harder, but not too bad. What I'd like you to do right now, just quickly, is take a look at worksheet number 7. Worksheet number 7, we've skipped worksheet number 6 just because of the way that I presented it this time. Worksheet number 7, questions 1 and 2. It should take you about 1 minute to do questions 1 and 2. If you want to draw the vector diagrams like I have in my 2 examples here, feel free to do that. But I wouldn't take off marks if you didn't draw the vector diagrams for these questions. All right, I'll pause this and give you about 1 to 2 minutes to try to tackle those 2 questions. All right, let's take a look here at 1 and 2. I'm not going to draw the vector diagrams for these, but remember, if you do, you have to draw the vectors head to tail. Right? The head of the one vector to the tail of the next vector. The resultant vector, which is the sum of the vectors, the one that you're trying to find here, is drawn from start to finish. Number 1 here, 150 meters, 100 meters are both in the same direction. So we don't need to worry about doing any kind of crazy math for this. Add them up, we're going to get 250 meters. 250 meters to the east, if our reference frame is north, south, east, west. Number 2, we've got 150 meters to the right and 100 meters to the left, or 150 to the east, 100 meters to the west. We add these ones up. We're going to get a total of, what's the answer to this one? What is it? 50 meters. Good. Positive 50 meters, or you could just say 50 meters. Good. Okay, easy. Well, a little harder. The second one is, but still not too bad, I don't think. Let's make it a little harder still. We did an example of this on Friday, but this is a little bit more of a challenge for us, okay? If we're going to add 3 plus 4 meters, but they're not on the same axis, one's on the east-west axis, one's on the north-south axis, well, now's when we have to draw our vector diagram. You see the rules that I followed for this vector diagram are still the same as I did for the last 2 questions. My 3 meters has a line with an arrow on the end of it, so does my 4 meters. And when I add these together, I'm drawing them head to tail, the head of the 3 meters to the tail of the 4 meters. Now, I could draw that a little bit differently as well. I could draw that 4 meters plus 3 meters. That would be fine, because that's drawn head to tail. Doesn't matter what order we draw them in, as long as they're drawn head to tail. What I couldn't do is this. Okay, I can't do this. How come? What's wrong with this one? What's wrong with this one, Ted? Well, they're going to collide, yes, but what was the rule again? You're drawing a vector diagram, the vectors have to be drawn head to tail. And this one is drawn head to head. So we can't draw a vector diagram like this. We also can't draw it like this. There's my 4 meters. There's my 3 meters to the east. What's wrong with this one? Yep. This one's tail to tail. If I'm going to draw a vector diagram, I have to draw it head to tail. That's what I did in the first 2 questions, although we didn't really need to draw the vector diagram in either of these questions. I did draw them, and they were both drawn head to tail. The 2 diagrams that I have drawn here are also drawn head to tail. Both of these would work. I'm going to solve the first one, however. Second will give you the same answer, but I'll just solve the first one here. Now, I'm missing something here, okay? I've got my 2 vectors drawn head to tail. The sum of these vectors, or what do we call the sum of those vectors again? It starts with an R. The resultant vector. The resultant vector, the sum of these vectors, is not drawn from head to tail. That's the one that's drawn from start to finish. So the resultant vector is going to be drawn like this. I'm going to label that as an R. The resultant vector, that's what I'm looking to find, the sum of these vectors. And I'm going to label an angle down here. I'm going to call it theta. The angle theta is the direction of this vector. Remember, if I'm adding 2 vectors together, I get a vector. And vectors include magnitude and direction. So I need the value of r, but I also need the value of theta, the angle of the resultant vector. Now, where do I draw that angle? Well, I always draw it from the start. Okay, you look at it, we're not going to draw it here because that's 90 degrees. We're not going to draw it here because that angle would be like from the finish. If you're giving somebody directions, you don't give somebody directions from the finish line. You give them directions from the start. So I'm finding the hypotenuse here. I'm finding the value of r. That's the sum of the vectors. And I'm finding the angle as measured from the beginning. Now, how do I find this value of r? Talked about this a little bit on Friday, right? We did one example, I think. Yeah, we're going to do the Pythagorean theorem. The Pythagorean theorem says a squared plus b squared equals c squared. So it doesn't matter which one you call a, which one you call b, but we know that c is the hypotenuse. It's r. So we're going to say if a squared plus b squared is equal to c squared, c would be the square root of a squared plus b squared. Or r would be the square root of 3 squared plus 4 squared. When I do the math for that, I get a value of 5. So we're saying here now, 3 plus 4 in question number 1 was 7. 3 plus 4 in question number 2 was -1. 3 plus 4 in question number 3 is 5. Now I'm going to calculate that angle. To calculate that angle, I got to pull out the calculator, do a little bit of trigonometry here. Remember, there's 3 basic trig functions that we have to know in Physics 20. There's sine, cos, and tan. If you remember, sine theta is equal to opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. And tan theta is equal to opposite over adjacent. SOHCAHTOA. You guys all remember that? SOHCAHTOA? When we look at this triangle up here, this right angle triangle, which side is the hypotenuse? That's the side that we always want to identify first, because it's the easiest one. Which side is the hypotenuse here? Is it the 3, is it the 4, or is it the red side, r, which is 5 meters? Yeah? Sorry? It's r, yes. It's the 5 meters is the hypotenuse. The hypotenuse is always the longest side. So I'm going to circle this and this in red because I usually draw my hypotenuse in red. You don't have to do that. If you don't have multiple colors for your pen or your pencil, whatever, it doesn't matter. Yeah, I'm just color coding it on the board here, okay? The hypotenuse, the longest side, is the value of r. Now, the hypotenuse is touching the angle. Look, the angle is drawn at the beginning here, and the hypotenuse is touching the angle. There's one more side that's also touching the angle. That's the adjacent side. That's the 3.0 meters. So we're going to say 3.0 meters is the adjacent. So two sides touch the angle. There's the hypotenuse, and there's the adjacent side. How do we keep them straight? Well, the hypotenuse is the longest side in the triangle, and the adjacent side is the other one that touches the angle. So now we know what the adjacent side is. Finally, the other one must be the opposite side, right? It's the one that's not touching the angle. There's only one side that doesn't touch the angle, and that's going to be the opposite side. So that's 4 meters in this case. It's not necessarily longer than the adjacent. It could be shorter than the adjacent. It's just the one that's not touching the angle. So the opposite side is the blue side here. Now, if I want to find theta, and I'm given the opposite and adjacent side, right? I am the 4 meters, which is the one that's not touching the angle, and the 3 meters, which is the one that is touching the angle and isn't the hypotenuse. Which trig function should I use? Which trig function has opposite and adjacent in it? Yeah, it's going to be tan. Now, because we're solving for theta, we're not going to say tan theta is opposite of or adjacent. Rather, we're going to say theta is the inverse tan, the second function tan of opposite over adjacent. The opposite side is, what's the opposite side, Gustavo? 4.0 meters. The adjacent side, I'll get your question in 1 second here. The adjacent side is 3.0 meters. And then we pull out our calculator to solve for theta there. I'm going to make sure that I'm in degree mode first. Sine 90 is equal to 1, sure enough. I'm in degree mode. And now I'm going to enter it into my calculator now that I'm sure that I'm in degree mode. Second function tan, inverse tan of 4 over 3, 4 divided by 3, and the bracket. When I do that, I get 53 degrees. Now, one more thing before I'm finished here. I'm so close. Now, when you're adding vectors together, you get a vector. Vectors include magnitude and direction. I've got a magnitude of 5 meters. I've got a direction of 53 degrees. Yeah, but what's the 53 degrees measured from? Relative to what? Well, it looks like here, the 53 degrees is relative to the east. I'm going north and I'm going east, agree? Right, if this is east, west, north, south, I'm going north and I'm going east with this resultant vector. But I'm measuring my angle from the east. It's touching the east, not touching the north. It's touching the east. But yet I'm going north from the east. So we're going to express this as 53 degrees north from east, or 53 degrees north of east. So in the first question, 3 plus 4 was equal to 7 to the east. In the second question, 3 plus 4 was equal to 1 to the west, or negative 1 meter. Here, 3 plus 4 is equal to 5 at 53 degrees north of east. Now, what if we had, just out of curiosity, what if I had drawn it like this? This would have been correct, right? I'm allowed to draw it like this because this is drawn head to tail. That's valid, right? Look, I want to find the value of r. Okay. I can find the value of r. R would be the square root of 3 squared plus 4 squared. Hey, look at that. That would give me 5 meters. Theta, drawn at the beginning, right, at the very beginning of the triangle, would be the inverse tan function of 3 over 4, opposite over adjacent. If I do the math on that one, I would end up getting 37 degrees. Wait a second. 53 degrees is not the same as 37 degrees. How can they both be correct? Go ahead. Yeah. Good. Good. So in this case, the second case here, my angle is measured from the north. It's touching the north, but yet I'm going east. So east from the north or east of north. Look, what's my position right now as I stand here? Well, I'm about 1 meter from the front of the room, but I'm also about 7 meters from the back of the room. Are those both not correct descriptions of my location, of my position? 1 meter from the front, 7 meters from the back. If Kaylee gave me, if I said, what's my position? Kaylee said 1 meter from the front. She'd be right. If Gustavo said, I'm 7 meters from the back, he'd be right. Well, why can't we say 53 degrees from the east and 37 degrees from the north then, right? It's the same thing. It's two different ways of expressing the same vector. Both are correct. If this is a quiz question or a test question, you get full marks for the first answer, you get full marks for the second answer. Just like Gustavo was right when he said I'm 7 meters from the back of the room. Kaylee was right when she said I was 1 meter from the front of the room. Make sense? How do you guys feel about that? All right, here's what I want you to do now. Take a look at your worksheet number 7, and I want you to work at your desks on questions 3 to 5. I'll walk around, ask questions. Look at the examples that you've done, that you've copied out. If you haven't copied this out, please do that before you start working on the questions. Look at the example here, follow it, and if you have trouble, ask me questions. All right, guys, I want to take a look at a couple of these here. Number 5, let's make a quick little copy of this so we have some space to work here. Sorry, number 3, I should say. So we get 20 meters to the east and we have 10 meters to the north. Is this drawn correct? Is this okay, you guys? Yeah, it's drawn head to tail, right? The head of the first vector, the tail of the second vector. It could have been drawn like this. That would have been fine, but it wasn't. Right? 3 plus 4 is equal to 7. 4 plus 3 is equal to 7. It doesn't matter what order we draw them in, as long as they're drawn head to tail. Now, the resultant vector, which is the sum of these vectors, if I say add these two vectors together, find the sum of these vectors, what I'm really looking for is the resultant vector. The resultant vector is drawn from start to finish, from the tail of the first vector to the head of the last vector. Now, let's label that as R. Don't forget, by the way, one of the common mistakes that people make with this is not putting a direction with this, right? They don't label the arrow on the end of it. They might draw it like this and say, okay, yeah, R joins start to finish. Well, that's going to get you the hypotenuse. It is. You're going to be able to use the Pythagorean theorem to solve for the value of R there, but you're not going to get the direction correct unless you label the arrow. You've got to label that arrow from the start to the finish. Make sense? Now, we also have to label the angle as well, because vectors plus vectors give me a vector. And a vector includes magnitude and direction. What's the direction of this value of R? I don't know, but I'm going to find that by finding the value of theta. Now, some people are saying, well, do I label this theta like from the adjacent side or from the hypotenuse, whatever? Look, the theta value is always measured from the adjacent towards the resultant. Got it? From the adjacent towards the resultant. Now, let's find the value of R here. How do I find the value of R? A squared plus B squared equals C squared, right? We're going to find the hypotenuse here using the Pythagorean theorem. So C is equal to the square root of A squared plus B squared. Let's do that on our calculator. Easiest way to do that, guys, second function, x squared. You see that little square root sign over the x squared? Now let's go 20 squared plus 10 squared. Press enter. I get 22.4, or to 2 digits, it would be 22 meters. Now, I'm halfway there. I've got the magnitude of my final answer. If I said, let's add 3 meters to the east and 4 meters to the west, well, the magnitude of that answer is 1 meter. The direction is west, 1 meter west. We need the magnitude and the direction of this one as well. Yeah, question? Yeah. Let's find the value of theta here. I've got the opposite side, that's the side that's not touching the angle, and I've got the adjacent side, that's the one that is touching the angle. So is the hypotenuse touching the angle, right? But that's not what I want here. Okay, the adjacent side is the other one that touches the angle. So I'm going to say theta is the inverse tan function, opposite over adjacent, 10 over 20 meters. On my calculator, now I showed you guys a little bit earlier that we want to do this sine 90 thing just to make sure we're in degree mode. You don't need to do that every time you do a calculation. Just do it the first time each day you do a calculation with an angle. So tomorrow, you'll do a calculation with an angle. Before you do, hit sine 90 and make sure it equals 1. If it doesn't, then switch your calculator to degree mode. Okay, I say sine 90 is equal to 1 here. I'm in degree mode. Now I'm going to go the inverse tan function of 10 divided by 20. So second function, tan, inverse tan of 10 over 20 gives me an angle of 26.56 degrees, or to 2 digits, 27 degrees. Now, I'm close. I'm almost there. Not quite. 27 degrees from what? Where am I measuring my angle from? Look, this 20 meters here is to the east. So I'm measuring my angle from the east. But which way am I going from the east? I'm going north from the east, right? I'm going east, then north. North from east, or north of east. So the answer to my question, when I say find the displacement here or add these two vectors together, is 22 meters at 27 degrees north of east. Somebody asked me a question as I was walking around. If this was a multiple choice question, what would be my answer? 22 meters or 27 degrees north of east? Well, they're both my answer. It's both a part of my answer, right? You can't separate those. Just like if I said, 3 meters to the east plus 4 meters to the west, what's the answer to that? Well, it's not 1 meter. It's not to the west. It's 1 meter to the west. The whole thing, the magnitude and the direction is my answer. Here, the whole thing, 22 meters at 27 degrees north of east, that's the magnitude and the direction. The whole thing is my answer. Let's do number 4. I know for some of you, I get this. I don't need to do all 3 of these questions. That's okay. We're going to do them anyways, just to make sure. Number 4. I get 15 meters. I get 10 meters to the south. By the way, is this vector diagram drawn okay? Gavin, is this drawn okay? Yeah, it's drawn head to tail. That's fine. The resultant vector will go from start to finish. Remember, draw the arrow on the resultant vector towards the finish. I'm going to label the value of r, and I'm going to label the value of theta. Where do you want to label theta here? I'm going to give you some options here. Where do I want to label theta? Position 1, position 2, or position 3? Which position should theta go in? Position 1, 2, or 3? 1, 2, 3. Theta? It's going to be position 3. Yes. And I'm going to do it in position 3 because that's the start of my vector diagram. Theta always goes at the start of the diagram. Now, let's find the value of r, or c in the Pythagorean theorem, right? C is equal to the square root of a squared plus b squared, or r is equal to the square root of 15 squared plus 10 squared. By the way, what do you think a common mistake would be when entering this into your calculator? What do you think a pretty common mistake would be? Say it again. Yep. Okay, so if you did this, then that would be a problem. Is that what you're saying? You don't put brackets in at all. Okay, so you actually don't need the brackets there. Let me just show you here. You could go second function, square root, right, the x squared button, bracket, 15 squared plus 10 squared, enter, and I get 18 meters. Okay, so this is absolutely correct, 18 meters. But at least if you have the TI-84 calculator, brackets are never wrong, okay, as long as you use them correctly, right? If you have the TI-84 calculator, I'm not sure if it works with the TI-83 or not, but you don't actually need the brackets. You can just say second function square root, 15 squared plus 10 squared, and you can see the square root kind of just carries over the whole thing. That's still going to give me the right answer, 18 meters. The common mistake here, guys, is forgetting to square one or both of those sides. You might go 15 squared plus 10 instead of 15 squared plus 10 squared. All right, I want to find theta. I've got this 10. Which side is the 10? Is that opposite or adjacent? It's not hypotenuse, right? The value of r is my hypotenuse. So is 10 opposite or adjacent? Opposite. 15 is? Well, which trig function goes with opposite and adjacent? 10. So I'm going to say theta is the inverse tan of opposite over adjacent. Now, I'm not going to check my calculator again to make sure I'm in degree mode. I know that I am. I did my sine 90 thing. Do that once a day. Okay, once you've done it, once you know you're in degree mode, let's just go inverse tan, second function tan of 10 divided by 15. Gives me a value of, to 2 digits, it would be 34 degrees. But 34 degrees, what of what? Where am I measuring my angle from? Look, I'm going south and east, right? But I'm measuring my angle from the east, but yet I'm going south from the east. So what would be my angle here? 34 degrees south from east or south of east? 18 meters at 34 degrees south of east. Now, you could have drawn it like this. You wouldn't have, because I already do the diagram for you in the worksheet. If you had of, you would have gotten a value of R that's 18 meters, but your angle would have been 56 degrees. But it wouldn't have been 56 degrees south of east. It would have been 56 degrees east of south. Make sense? Okay, one more. Number 5. I got 10 meters to the west, 5 meters to the south. Is this drawn correctly? Yes, it is. Okay, it's drawn head to tail. My resultant vector should go from start to finish. Good? Is that good? Kenzie? No, what's wrong with that? That's correct. Like, I've got my red line drawn in the right place, but not in the right direction. It should be drawn from start to finish. The arrow should be on the other end of it, indicating start to finish. Is that right now? Is that good now? Yes. Let's label R here, and let's label theta. Where am I going to label theta here now? Position 1, position 2, or position 3? Where does theta go? 1, 2, or 3? 2. It's position 2. Always drawn at the start of the diagram. You give them directions to somebody, give them the directions from the start, not from the finish. And then the other one, of course, this is just our 90-degree angle, so it's never going to be the one we label. All right, let's find the value of R. It's the square root of 10 squared plus 5 squared. What if I did it, what if I had done it the square root of 5 squared plus 10 squared? Would it make a difference? No, it doesn't matter what order you do it in. Okay, let's do this on the calculator. Second function, x squared, which is square root. Now, use brackets if you want here. 10 squared plus 5 squared. But make sure you end that bracket if you're going to use brackets. Gives me a value of 11.18. The 2 digits, it would be 11 meters. So 10 plus 5 is equal to 11? Yeah, it is. At what angle? R is my hypotenuse. 10 is my adjacent, because it's touching the angle, but it's not the hypotenuse. 5 is the opposite side. So I got opposite and adjacent. The trig function I'm going to use is tan, but I'm solving for theta, so it's the inverse tan, or second function tan, of opposite, 5 is the opposite, over 10, the adjacent. And again, I don't need to do the check on my calculator again to make sure I'm in degree mode. Just go second function tan, 5 over 10. Now tomorrow, when you work on a question like this, do the check once. Go sine 90, make sure it equals 1. Just to make sure, once a day. The inverse tan of 5 over 10, I get 26.5 degrees, or 27 degrees. 27 degrees what of what? Enter. Where am I measuring my angle from? From the east or from the south? Sorry, that would be west and south, right? And I'm measuring it from the west or from the south? From the west. But yet it's going south from the west, right? So we're going to say south from west, or enter, not west from south, right? This would be west from south. South from west, or south of west. Yeah, does that make sense? South of west. Does it feel, you guys? Comfortable with that? Okay. Well, let's try this then. An even harder question. 5 meters plus 4 meters plus 2 meters plus 2 meters plus 1 meter. But the 5 meters is to the north, then the 4 meters is to the east, then to the south, then to the east, then to the north. Ooh, this one looks nasty. It's not really that bad. Trust me, it's not really that bad. In these last few questions that we've done, we've had a right angle triangle. That's the goal. We want a right angle triangle so that we can do the Pythagorean theorem and the inverse tan function. That's what we want. I've got a vector diagram here drawn, and this is a good vector diagram. You can see that all of the vectors are drawn head to tail, head to tail, head to tail, head to tail. Those are all drawn well. But when I draw the resultant vector from start to finish, right here, I don't have a right angle triangle. I don't even have a triangle, let alone a right angle triangle. So how do I get the goal out of this, the right angle triangle goal, so that I can do what I've just done, the Pythagorean theorem in the inverse tan function? Watch carefully here, guys. I've got to break this up in what we call x and y components. This is x, the x-axis. This is the y-axis. So break it up into x components and y components. Don't take shortcuts. Every single time you get a question with more than 2 vectors in it, do this. Make an x column and a y column. Let's look at each of the vectors and identify how much of each of the vectors is on the x-axis and how much is on the y-axis. So let's look at the 5 meters first. How much of that 5 meters is on the x-axis? Riley, how much of this 5 meters is on the x-axis here? 0. None of it. It's all on the y-axis, right? So I'm going to put 0. Riley, how much of it's on the y-axis? 5 meters. So there's my first vector. None of it is x. All of it is y. Let's look at my second vector, the 4 meters. Leighton, how much of that 4 meters is on the x-axis? The horizontal axis. Pardon me? 4 meters. Good. How much of it is on the y-axis? 0. 0 meters, right? Look, it's all x-axis. That makes sense? None of it is y-axis. Next one, the 2 meters, the third vector. Gustavo, how much of that 2 meters is on the x-axis? 0. It's all on the y-axis, right? 0 is on the x-axis. Ooh, here's a tough question. See if you can get this one. Tricky question here. How much of this 2 meters is on the y-axis? Anybody think they have this one? How much of this 2 meters is y-axis? Yeah? Negative 2 meters. Good. Why do you say negative? Good. Because it's going down. Negative 2 meters because it's going down. How much of that next one, the fourth vector, is on the x-axis? Taya, how much of this 2 meters is on the x-axis? This one right here? Yeah, 2 meters, good. And how much of it's on the y-axis? 0. You understand the difference, guys, between 0, negative 2, and then positive 2, 0? Negative 2 because it's 2 down, and then the positive 2 here because it's 2 to the right. And finally, the last one, the 1 meter. The 1 meter, Ainsley, the 1 meter, how much of that 1 meter is on the x-axis? 0. And how much of it's on the y-axis? Positive 1, good. So far, so good? Now what I want you to do is add all the x's and all the y's. Zero plus 4 plus 0 plus 2 plus 0 is 6 meters. 5 plus 0 plus negative 2 plus 0 plus 1 is 4 meters. Now, watch this. I'm going to redraw the vector diagram that I had originally drawn here. Watch this. I got 6 meters to the east. And I've got 4 meters, 6 meters to the east and I've got 4 meters to the north. How did I know to draw 6 to the east and 4 to the north? Sorry? Yeah, so the 6 is positive, the 4 is positive, but how did I know, how did I know to draw this vector diagram, east and north? Like 6 and 4, that's for some of them, right? What I'm doing is drawing a vector diagram, not with all the individual vectors, but with the total east and the total north. If this had been -6 and +4, I would have drawn it like this. Now, is this correct, guys? Does this follow the rules of drawing a vector diagram? Sure it does. Head to tail. Now, look at the resultant vector here, you guys. Look at the value of that. Look at the resultant vector that I've got drawn here. Does it not look like the resultant vector that I do in the first diagram? It's the same thing. It's the same vector. But now I have it drawn as part of a right-angled triangle, which, remember, that's the goal. Get a right-angled triangle so that we can do our thing. This question at this point is exactly the same as the last example we did and the 3 questions that we just did on the worksheet. Now that I have a right-angle vector diagram. Yep. Yeah, that would be fine. You could have absolutely drawn, I didn't do that, but I could absolutely draw 4 meters, then 6 meters, because that's drawn head to tail, right? So long as you draw head to tail, it's all good. You get the resultant vector here. You get the same value of r, just your theta would be different. But that's okay, right? 1 meter from the front of the room, 7 meters from the back of the room, same thing, right? So I'm going to do it the first way, but you could absolutely do it that way, and that would be correct. By the way, I should label theta. Where am I going to label theta? Position 1, 2, or 3. 1, 2, or 3. Position 1, always at the start of the vector diagram. Okay, let's find the value of r. Square root of 6 squared plus 4 squared. What is that? Square root of 6 squared plus 4 squared is 7.2. So 6 plus 4, well, not 6 plus 4, really 5 plus 4 plus 2 plus 2 plus 1 is 7.2. At what angle? Well, let's say theta is the inverse tan function of opposite. What's the opposite side of the triangle here? The 6 or the 4? Yep, the 4, good. So it's the inverse tan of 4 over 6. On my calculator, the inverse tan of 4 over 6 is, to 2 digits, 34 degrees. I am so close to being done. Now I just have to express my frame of reference. 34 degrees, what of what? My angle is measured from the adjacent to the hypotenuse. The adjacent side is east. So from the east, but yet I'm going north from the east. So how am I going to express this if I'm going from the east, north from the east? Not north from east, but rather we'll call it north of east. 34 degrees north of east. Good? Ada, your question earlier, what if you had drawn the 4 then the 6? You would have gotten 7.2 meters, but you would have gotten an angle of 56 degrees. 56 degrees, it would have been east of north instead of north of east. How did I get that angle so quick in my head, that 56 degrees? I didn't do trig, right? I didn't do trig in my head. Yeah, it's always the complementary angle. The other one's always the complementary angle here. So 90 minus 34 is 56 degrees. If you get 34 degrees north of east, it's always the same thing as 56 degrees east of north. Guys comfortable with this? How is this different than the last 4 questions that we've done? This down here is exactly the same, right? But we had to get to this point, remember. What was the goal when we saw this funny diagram up here with all these different vectors up there? The goal was get a right angle triangle. And get a right angle triangle so we can solve it like the last 3 worksheet questions. But how do we get the right angle triangle? This is where we have to break it into x's and y's. Look at each vector. How much is x? how much is y? Then add them together and redraw it with the total x and the total y. Now you get your right angle triangle, do your Pythagorean theorem and tan function. Good? All right. Now, then, if you're comfortable with that, I'd like you to take a look at worksheet number 7, questions 6 and 7, please. Worksheet number 7, questions 6 and 7.